This is going to be a talk about Exposed, an open source database access library that's been publicly available since 2016 as a JetBrains team project. Before becoming open sourced, Exposed was created as a tool by JetBrains employees for internal use on other products. And for the majority of its existence after this point, it was maintained primarily through the contributions and efforts of a single individual in their free time. Exposed started with a single core module, and then 2 extra modules were added to allow Spring integration. And in spite of all this, the library started to get attention, and the amount of external users started to grow to the point where today it is the number 6 most starred out of all JetBrains GitHub repositories, and that is in spite of it being the only one in the top 10 that doesn't hold official JetBrains status. So in 2023, the team that I'm a part of was established to work full-time on maintaining and improving the library. And one of the major tasks that we had was addressing the massive backlog of GitHub issues. So far, we've brought it down by about a half. Majority of those issues were long-standing feature requests, as well as quite a few Spring Transaction Manager design issues, and some of our own roadmap points, like addressing our query DSL design, some performance issues, and getting the ball rolling on providing database migration assistance. And it's really important to note that this progress over the last year, not every single issue that was addressed by a member of the team. Between our first team release and our most recent release, we've had 43 new contributors. And I think it's really important that I mention, and on behalf of the entire team, thank you to everybody who has continued to give support to this library in the last year and the year before that, because community support, contributions, public feedback is very vital to us. And it's been vital to our progress moving forward, particularly for our goal this year being our first stable release version 1.0. So I'm here today to give a very introductory overview of 4 things. What the pain points are of database access, that why you would use Exposed, how to get up and started using Exposed, why Exposed has exciting potential as a versatile tool, and where Exposed is headed. So let's get started with what are the reasons for reaching for a tool like Exposed. On the left, we have a Kotlin developer building an application, and on the right, we have a database. And at some point, the app and the database need to interact with each other, sending and retrieving data. What exactly the bridge between those 2 layers looks like can be very different depending on the needs of the developer and the specific needs of the app. Maybe, as a developer, you just want to focus on manipulating data without having to use SQL, and you want to easily map your database table records to your existing Kotlin objects. Maybe you have so many tables with so many relations, you don't want to be concerned about the intricacy of how you're joining those tables or how you're loading references. And maybe it's really important to you to not lose time and productivity in your team learning a brand new complex framework that on top of that would require you to do things like use annotations or alter your existing Kotlin data classes. Maybe none of those actually apply to you, and you actually want some control over your SQL interactions, whether it's for complex queries or for batch statement executions. But you still want to do so in a Kotlin type-safe way that doesn't hide the SQL and still gives you the option to validate what exactly is being sent to the database, while still giving you the freedom to have as much or as little control over the generated SQL strings. Maybe on an even lower level, what you actually just want is a tool that allows you to write and run SQL in the way that you want, with the parameters that you want, and handle and process the result sets in the way that you see fit, without dealing with low-level tasks like opening and closing your database connections, committing and rolling back your transactions, and wondering whether you're actually releasing your resources properly. Ultimately, what is best between those 2 is an abstraction layer, and how high or how low that abstraction sits is a choice, and Exposed provides you the flexibility to help you make that choice. And if multiple database connectivity options is a requirement for you, Expose provides a consistent API that abstracts away any of the underlying database differences, leading to the ability to write a query once and have it be translated and handled appropriately depending on the underlying database. Our mascot is a cuttlefish, and much like the cuttlefish, Exposed is able to sit on top of multiple databases and switch between them with little to no effort on your part so you can focus on building an app that is database agnostic. So how do we get started with Expose? The first question being, we have a database, we want to interact with it, how do we set up a connection? Database connect is a function that creates an instance of a class that represents the database being used, and it accepts a connection URL or a data source. Expose relies heavily on the API loaded by Java database connectivity drivers for the underlying database system to actually establish connections. And if there's any special configuration parameters that need to be configured for all database connections, they can be set in the database config builder here. But what's important to note about this function is that even though it's called connect, at no point by simply invoking it are you actually creating a connection. Invoking this function just provides Expose with the details to actually establish a connection the first time it's required later on. And if you need multiple database connections, you can call the function multiple times and store the instances in variables for future qualification. So we have a way to establish a connection to our database. What about the data model in our app on the other side? How do we map that data to our database records, and what model are we even going to use today? The original GitHub Expose wiki used this model significantly in samples, and it still exists in a lot of our legacy documentation. So today, we're going to follow through with a sample app. The source code will be available at the link after the talk, where we're going to imagine that we're in charge of a bunch of docking bays, hangars for short, and we have clients from off-world that are going to land and store their ships in our docking bays, so we need to record data about the ships and the planets that they originate from. So we start with a data class that stores the details about our planets that we're interested in. How are we going to map this data class to a table object? The table class in Expose is the core class for database schema definition. It holds multiple methods to register different column types as well as specific table properties. So for example, we are first going to register a column that accepts long values. We're going to declare that column should increment automatically on the database side with every newly inserted record, and we're going to set that column as the table's primary key. Then we add another column for strings up to a certain length, another column that accepts enum constants, but on the database side, it's just storing those enums by their ordinal values, and lastly, a column that accepts doubles. So if we imagine that every ship that lands comes from only one planet, and obviously a planet can have multiple ships, this is the data class for storing our ship information. It stores, in addition to that, our planet details, and actually in the database, this is the one-to-many relation that we're trying to establish between the planets and the ships table. So once again, we start with our table object. We still want our now holding an integer column to be our primary key column, but we don't want it to increment. We just want to establish a constraint in the database that checks to make sure that the value being inserted is between a certain range that matches our existing docking bays. We add another string column, but this time with a unique index constraint. Another string column that accepts null values in the event we choose to leave a ship type as unclassified. And another column that accepts dates and defaults to the current date. And then finally, our reference column, with the reference method creating a foreign key constraint on this table and storing the ID of the associated record in the planets table. So we have a means to connect, we have our data model. How are we actually need to create our tables now. And to do a unit of work in a database, we need to open a transaction. So the transaction function accepts the instance of the database that we want to use for connections, And in the Lambda, we can do any data definition and data manipulation operations that we want to, for example, creating our tables. The schema utils is just an object that holds multiple utility functions for creating, altering, and dropping different schema objects. And so with the two table objects and that create, we're able to generate the SQL for our planets table and the SQL for our ships table with all of its constraints. And if on top of that we had multiple different database connections, Expose would handle any syntax differences for us. And this works well if, for example, you're starting from scratch every time. Maybe you have a connection for a database that's used for testing where you start up a database every time. But what if you have an existing database? What if you have a database in production that potentially changes over time? There is an alternative, create missing tables and columns, that first checks the current state of your existing database tables, generates any create and alter statements to make it fit the mapping defined by the exposed table objects. And additionally, if there are any other inconsistencies, it can log them and suggest SQL fixes. So the transactions that we've seen so far have been fairly simple, but actually in their simplest form, we can omit the database argument passed to the transaction function. And in that event, how do we even establish a database? What database is being used in the transaction block? If database connect was called only once, the transaction manager associated with that registered database instance would ensure that that instance is implicitly used every single time a transaction block is created, because that instance would be the last and only instance that was defined. If we were in a situation where we had multiple instances stored in different variables, we can manually set the default database so that if we choose to omit the argument from the transaction block, we can trust that that default will be the one that is used by that transaction block. And in its full form, the transaction function actually accepts multiple other arguments and has many properties that can be changed for that local transaction instance. And if any of these properties are set for a specific transaction, it overrides any of the default transaction settings that were configured when you called Database Connect for the first time. So we've created our tables. Let's actually insert some data. We already have in the app 9 ships docked, and we have some information about them. But now we have a new ship coming in. We're going to put it in docking bay 3. That ship comes from Geonosis, and it turns out we don't actually have Geonosis in our system yet, so we both need to insert the new ship data details before inserting the new planet details before inserting the new ship details. All, or the majority, of SQL commands are available as extension functions on the table class. So we call insert on our planets. We insert by assigning new values to it being the insert statement, by setting the new value to the associated column type, or the associated column in the table. Insert also allows us to return that statement so we can access any of its properties, which is important because we need to get the auto-generated key that was incremented on the database side. So we get the planet's ID and we store it in a variable. And it's important to know that obviously we got that auto-generated key, we can actually omit values, so we don't need to assign anything that is database generated. So we've managed to input a new planet class. Now we want to actually insert data for the ship. We call insert again on the ship's table. We once again assign new values to the columns. We once again can omit certain columns like the arrival date because that is defaulting to the current date, and we provide the new planet ID to the origin planet column. And we see that we have a 10th ship, a new record in our results. So we have some data, let's actually query it. What if we wanted to filter all ships that were docked by the planets that they originate from that start with COR and actually comes from the core worlds? We see we have 2 options from 2 different planets. If we query the actual planets table just to confirm that those are actually the only planets that match that condition, we once again start with an extension function, select all on the planets table that both instantiates a query and selects all the columns in that table. We add a where clause with the conditions that we've specified, and an order by clause. And the important thing to note is that this way, with query building with expose, we could continue to chain as many clauses as we want, and at no point is the query actually sent to the database until some terminal operation is chained that attempts to iterate over a result set. So now, if we call to list, our result chains to a list of result row, with result row just being a class that represents a single record from the database result set. And if we look at the SQL side by side with the query, we see that it pretty much aligns, with the major difference being how expose chooses to anchor and start a query on the table object that we are focusing on. We have our query again with our results. If we wanted to map those results to our data class, we could provide a conversion function that accesses the stored values of each column in each row, and then we could provide that conversion function to another terminal operator like map, and we would get back a list of our data class instances. Now, what if we wanted to query something a little bit different? We actually wanted to get details from both tables. For example, all ships that are unclassified arrived in the last 3 days, and we want to sort in descending order by hangar ID. We first start with our date for 3 days ago. It's just a local date. We have a left join on our ships table that gets all records from the ships table that has a match in the planets table based on the foreign key. We once again select, but we're only selecting the columns that we're interested in from both tables. We add a where clause. I'm going to just move this up so we can see a bit better. We add a group by for the 2 keys in both tables. We add an order by in descending order by hangar ID. We call to list to send the query to the database, and we get our results. And looking at them side by side, the clauses are aligned, and majority of the join syntax has been reduced because the left join infix function tells expose to implicitly join on the primary key and foreign key columns from the 2 tables. And we get the same results that we got in our app. Now, what if we wanted to update multiple records? Let's say, for example, we filter all dock ships that are unclassified. We get quite a few results. We can see those again here. What if we wanted to have every record that has a null ship type, we want to give it a generic string type? Once again, an extension function on our tables object we call update. To achieve the update that we want, we're going to use something called coalesce, which is an example of an exposed expression that maps to a database function that essentially says return the first non-null value, either what is stored in the ship's type column or the string. Just like with insert, we're assigning this new value to the update statement using the associated column. And we see that we no longer have any records that have a null ship type. An update also returns, but it doesn't return the statement. It returns a count of updated rows after the statement was executed. And now if you want to do the same thing, we want to delete multiple records that have a certain condition. Let's say all the ships that are shuttles are leaving today. So we want to remove those ships from our system. We have 2. We can see those 2 here as well. We call delete where on our ships table. We provide the string pattern matching clause that we're interested in. And we see that we've gone down 2 records. And delete where like update returns a count of deleted rows. So the examples that we've seen follow the domain-specific language approach, which is available in the core module and aims to provide type-safe SQL in a way that still feels and reads like standard SQL. But there is an alternative. You can instead provide a dependency on the data access object module, which is still type-safe but less verbose and isolates away even further the underlying implementation for how the data is being accessed. If you play around with the actual app source code, both approaches are available through a common interface. There's 2 files for 2 different implementations, one for DSL, one for DAO, and we can actually switch between the 2 approaches by changing a property in the application conf file. And other than the differences between those two files, the data access functions in those files, the main difference that we're going to see is how we map our data models to the actual database table objects. So this is our original planets table. We're going to refactor it to work with DAO. We no longer need to define a long column that auto-increments or primary key ourselves, because we're going to extend a long ID table, which is just a subclass of the base table class that does that for us. And then no other changes are required. But this ID table needs to be associated with an entity, because every database record in the planets table needs to be mapped to an entity by its primary key. And the primary key is wrapped by a special wrapper class, entity ID, which is just used internally for distinguishing it and for some internal logic. And then every entity is managed by an entity class, which is responsible for maintaining relations between the entity and the actual table object. And then each entity has a field that delegates to the table object columns. So if we do the same thing with our ships table, this is the original ships table. The difference with this one being we're going to extend directly from the base ID table class because we don't want our original integer column to auto-increment. We want it to be the primary key and we want it to be the ID column, but without auto-incrementing, all we have to do is instead call entity ID to make sure that that original column is wrapped properly for the ID table. And the other difference being in our reference function, we no longer need to pass the ID column of the planets table. We can pass the entire planets table itself because it's now an ID column and we can trust that it's now an ID table and we can trust that it has an ID column that we can use. And once again, we have an entity for every ship record that's managed by an entity class. And we have entity fields that delegate to the ships column. The reference field is going to look a little bit different. We use an infix function referenced on, which registers the foreign key constraint in the ships table and stores the field value as a mutable planet entity. So we're no longer just storing the ID of the associated record. We're storing the entire parent entity for that child with all of its fields available. So now that we've defined our DO tables and our entity classes, we're going to try to perform some data access functions, and we're going to see that we're no longer going to be using extension functions on the table class. We're going to put the table class aside. We're going to be performing functions directly on the entity class. There's no longer an idea of insert, statement, or columns. Instead of saying insert onto planets table, we're now just calling new on the planet entity. And instead of assigning a value to a column, we're just assigning a new value to an object field. We can once again, of course, omit certain fields like the ID that increments on the database side. And new also returns. It returns the newly created instance that we can use when we're going to insert a new ship. So we have new on a ship. We're providing the new planet entity that we just created to the origin planet field. We're once again omitting the arrival date field because it defaults to the current date. But the ID looks a little bit different because we're manually providing the ID. So when we manually provide an ID to the new function, we have to actually pass it as an argument because unlike the other fields in an entity, we are assured that the ID field is always immutable. So it has to be passed as an argument. We can't use a field assignment. So now that we've inserted, let's query. Let's say we wanted to get all ships from planets with a distance roughly between 10,000 and 30,000. We see that there are no records that match that. But if we query the planet table itself to confirm that, we can see something else. And when we're querying with DAO, we are no longer returning a result set with columns and stored values. We're actually returning the entire entity instance with all of its fields. We're no longer doing a select all because, like I said, we're returning all the fields. So we just do a find on the planet entity. We provide the condition that we're interested in, and even though we're using DAO, we still have access to all the DSL core functions, operators, and expression builders that we need. And like with DSL, we could continue to chain onto this query if we wanted to, and it wouldn't be sent to the database until we perform a terminal operation. So if we now call to list, we get the results. And if we still wanted, on top of the fact that we already have entity classes, if we still wanted to map these entities to our original data classes, we could still do that by accessing the entity object fields, with the one thing being a little bit different being our ID field. Because if you remember, the ID is wrapped by a special entity ID class, so we just need to access the internal wrapped value to actually get the long value. And then we just provide that to our terminal operator map, and we get a list of data class instances. And once again, if we want something that actually gets both details from both tables, say we just want to get all ships from a particular planet, let's choose Dathomir. If we were doing DSL like before, we would perform some sort of a join, send that query to the database, and get the results. But one of the strengths of DAO is how it handles table relations by performing joins for us. So if we have the original planet entity, to make it give us the same results as DSL, we just need to add one new field, the ships field, that uses the infix function refers on, which registers a foreign key constraint on ships as an immutable collection of child ships that reference the parent planet. So now, to get the same results, if we happen to have, for example, the entity that we're interested in, maybe we used another DAO function like find by ID with the ID, we have the parent entity. To get the list of ships that originate from that planet, all we need to do is access the new field that we added and call to list. And we have our results. Now, what if we wanted to update a single record? Let's say that the ship that we put in docking bay 3, they weren't actually using their own license, they were using somebody else's, and now they have a new one, and we need to update that. If we were using DSL, we would use the same update function we saw before with a where clause specific for that record, and we would assign the new value to the column. But if we're able to access a database value by accessing an entity object, surely we can set a database value by setting a database object field, which is how updates work with Expose. We just assign the new value to the entity's objects field. And we can see that we have an updated record in our system. The important thing to note about doing updates this way with Exposed is that these updates are not sent to the database automatically. They are instead scheduled for a later time and stored internally on the entity cache. This is one of the ways that the DAO approach attempts to minimize multiple database operations being sent for every data manipulation by accumulating and then caching this value until it's absolutely necessary to send it to the database, which usually happens either before something like a select all query is run. If we either just say manually flush everything, send everything scheduled to the database, and if neither of those things happens, at the end of the transaction block. And now let's say that we wanted to go in, the ship from docking bay 3 has left, we want to manually delete that. If we were using DSL, we would just use the same delete where that we saw before, but with a clause particular for that row. Deletion is very straightforward in DAO as well. We simply call delete on the entity that we have, and it both clears it from the cache and from the database record, and we can see that we've dropped down one. So we've seen the core DSL. We've seen how DAO builds on top of it, deviates, does its own thing. But there is a third way that I think really shows how the Expose shines, and I like to think of it as the DIY, the do-it-yourself way. Because ultimately, this library was built by Kotlin developers for Kotlin developers, and it was built with the best of intentions to allow you to access data in the way that you want to. So I'm going to very lightly touch on 3 ways that Expose allows you to tailor your experience using it to your specific needs. The first being actually taking advantage of statement interceptors. Let's say, for example, we want to gain more control over a statement's lifecycle by adding extra functionality at specific points. If every time a ship is removed from a docking bay, we want to update that docking bay's logs to include information about the ship that just left, we add a custom class that extends the statement interceptor, implements the statement interceptor interface. This interface has many functions. This is only 3 of them for different points in the lifecycle of a statement, and the only one we're actually interested in is what happens after execution. So after every statement is sent, we're going to check and see, was that statement a delete? If it was a delete, we're going to call our special function log deletion, and we're going to pass some transaction and statement and timestamp details that we're interested in. And if you go through the source code, log deletion just performs some operations on a shadow table of sorts that we can query later. And then to actually use our custom interceptor, we create an instance of it wherever we want. I just put it in the transaction block for simplicity's sake. This is the transaction block that wraps every data access function in the app. We register and we unregister it when we're ready. So in addition to adding extra functionality, we're also choosing exactly when to turn on and off this extra behavior within our transaction block. And if we're using the DAO approach, there's a very similar concept, but it uses entity hooks that allow you to subscribe to particular phases of an entity's life cycle. So in our case, we would be subscribing to when that entity is both removed from the cache and from the database. We would call our same function, and we would get our same results. Another way to get more out of Expose is just to run plain SQL commands directly. If you know what it is that you want to send to the database, Expose lets you do it. So we can filter ships based on distance. The upper bounds for the range slider that we used is based on the current furthest away planet that we've encountered so far. So every time we insert a new planet, we want to call a stored function that retrieves the actual maximum distance so we can use that as the upper bound of our slider. To run plain SQLs, you just use the exec function, which in its simplest form takes an SQL string and just sends it to the database. This is the SQL string that we're using. I've split it into 2 to make it easier to read. The first part just creates a function, provides an input parameter for precision, and returns a numeric value. The actual body of the function selects the maximum value from the distance column, rounds it to the precision that we specified, caps that value at a maximum, and then returns that result. Then to actually call our function, we're going to use exec in its more complete form. We're going to provide the SQL string that calls the function with a placeholder for the parameter. We're going to provide an argument for that parameter as well as a column type that tells Expose exactly how to process the parameter when it's setting a prepared statement. And then we provide anything that we want in the transformation block. So in this case, we could just iterate over the result set and transform the result and return whatever we like in this block. And then for convenience sake, we're going to wrap this entire exec as an extension on the transaction class so that we can use it wherever we want with whatever precision value that we want. The last versatile thing about Expose I'm going to touch on is its ability to be customized. Whether it's for an unsupported data type, an unsupported operator, or function, almost every class in Exposed is open for extension. Let's say we want to add a detail to our planets class. We want to be able to see every time we look at a planet what the price range is that we could charge for a ship originating from that planet. If you remember, we're using Postgres. So we're going to have a custom column type that accepts a Kotlin int range. The first override just defines what the SQL type is for Postgres. This is int for range. The second override declares how to transform the int range into a valid SQL string value. And then Because Postgres has a stricter type system, we have to also override set parameter, and there's a lot of code there. The only important lines are these, which essentially says each time you prepare a statement, make sure that you set the parameter as a PG object with this exact type and this exact string so that the database doesn't throw any class cast exceptions. And then all we need to do is override one more, which does the reverse, that says every time we retrieve a PG object from the database, this is how we transform it back into an integer range. And then all we have to do is create an extension function on our table class that allows us to register a new column type. And we can now add that column to our existing planets table. We can even give it a default value, for example, and just like that, we're able to insert ranges into our planets table. And of course, if you want to get the full power out of a new column type, you probably also want to customize your own operators and your own functions, and some examples of that have been included in the app source code if you're interested. So we've covered a very introductory level overview of what the current state of the library is. We're going to wrap up with where Exposed is headed by looking at some roadmap highlights that we would like to share with you. We've put a lot of effort into improving our documentation, particularly adding all missing KDocs from the public API. We've also given a lot of attention to our original GitHub's wiki, and we've actually moved it into its own GitHub Pages site. But we still have a lot to do. We're still committed to providing significantly more tutorials and samples and syntax mappers. So improving documentation is an ongoing task that we are continuing. The call for migration support has been heard. As I mentioned earlier, we already have introduced a way to generate a migration script from the existing table objects. But on top of that, we're now going to go forward and do more tasks, like, for example, addressing some of the current limitations that we have by specifically fleshing out some of the functionality for dropping schema objects, for example, which initially Exposed took an opinionated stance against. And we're also going to add specific modules that allow easier integration between Exposed and more mature migration tools like Liquibase and Flyway. There are currently quite a few tasks underway for IDE tooling, with the overall goal being to make it easier to get up and started using Exposed and to reduce boilerplate code overall. One of the first ones is, for example, if a database already exists, then making it possible to actually auto-generate the Exposed table objects that I showed you based on the existing database objects. Another big one is generating the entity classes that I mentioned. When I was talking about DSL, I said it was less verbose, and then 2 seconds later I said for every ID table that you have to have an associated entity class. Our goal is to take that task away from you and for the IDE to auto-generate these entity classes for you, at least at a base level, because I could spend an entire talk talking about how important the companion object is in an entity class, but the fact is majority of users do not need to override anything in the companion object. They just need the base entity class, and we're going to work on doing that for you. Another one that we're working on is creating data sources in the IntelliJ database tool window, so that based on the specifications that you mentioned in your database connect function, it automatically creates a data source that matches that. And the last one being out-of-the-box live templates for common Exposed code constructs, so that you have to write less code. And the last major roadmap highlight that I'm going to touch on is R2DBC support using Kotlin X coroutines. I mentioned right at the beginning of the talk that Exposed relies heavily on the API loaded by JDBC drivers, and those drivers are blocking. So we are committed to providing support for the non-blocking variants, for the reactive relational DBC drivers, so that Exposed can work better with databases using asynchronous operations. This will also give us an opportunity to work on some of the current limitations and some of the current issues that we have with the state of our suspend transactions. So thank you for pulling through with me for the last, 40 minutes while I covered the basics out-of-the-box functionality of Expose, what it has to offer, both its extensibility, and we went over some 2024 roadmap highlights. There's probably time for questions. But otherwise, just to note, myself and another member of the team, we will be available at the JetBrains demo booth after this for about 2 hours. So if you want one-on-one time or you just want to chat more about Expose, please come find us and we can chat some more. Thank you for listening, and I hope you enjoy the rest of the conference.